Hello and welcome to this introduction to hybrid powertrains. My name is Per Marklund and I'm the one who will try to guide you through this quite advanced subject. In this lecture we will go through different parts regarding hybrid powertrains. We will start with a definition of the hybrid powertrain. We will talk about when hybrid technology is beneficial. We will go into different types of hybrid trains and explain how they are built up. Series hybrid, parallel hybrid, and also what is called a plug-in hybrid. We will discuss what different combustion engines that are normally used and why. And we will just quickly go through how the electricity is stored. So what is a hybrid powertrain then? A hybrid powertrain is a combination of two or more motors in the same powertrain. Normally, this means that we have an internal combustion engine, which we will call ICE in this presentation, in combination with one or more electric motors. This is the most common case. The definition of a hybrid powertrain, however, can sometimes be misused as a combination of different energy sources. For instance, if you have batteries in combination with a fuel cell that powers an electric motor, sometimes that is also called a hybrid powertrain. But by definition, it has only one motor, the electric motor, so it shouldn't be called a hybrid powertrain. This is, however, maybe weakening up the definition a little bit, so let's see in a few years if we have to revise this definition. The hybrid technology then gives a possibility to have a higher performance in combination with a lower fuel consumption when you combine a small internal combustion engine and a large electric motor. The storage of the excess energy from the ICE in combination with the generator and also recovered brake energy is stored in the accumulator, or maybe in some cases a supercapacitor. However, nowadays the supercapacitor isn't very often used and the accumulator with the lithium-ion technology is the normal case. So the basic idea then is, if you compare this to a normal standard ICE type of powertrain, you don't often need full power in your vehicle during a longer time of driving. And the average needed power is much less than the maximum generated power from the ICE. So if you have a hybrid powertrain, the ICE then has to be around the average needed power of the driving cycle. But with an ordinary ICE powertrain, the ICE has to be the maximum needed power. And this even if you only use it now and then with the maximum power. And this means that you have a bad utilization and bad efficiency. So with the hybrid technology then, when not all the ICE power is needed, the excess energy is stored in an accumulator. And when more than the available ICE power is needed, you consume the energy stored in the accumulator. So you can have higher power output than what you have from only the ICE. If you look at the internal combustion engine, the ICE, and we look at it from a brake-specific fuel consumption diagram, which is what we can see here, sometimes called the muscle diagram. We can see the engine speed on the x-axis and the engine load with the definition of BMEP, brake mean effective pressure. You can see this as the torque output as well from the engine, if we simplify it a little bit. This means that you have the highest efficiency, as you can see on these contours, when you have in most engines, when you are around 2000 RPM and you have a high load, maybe not the maximum load, but maybe 85% of the maximum load. This means that if we could utilize the engine in this operation point, this RPM and this load, we would have a higher efficiency, so we will get most energy out from a liter of fuel, basically. And if we then have a hybrid powertrain, we have the possibility to control this, so we utilize the engine in the most efficient way, which is not always possible if you have a traditional drivetrain, where you have to have an engine that's basically too large to most of the situations you are driving in. If you look into driving cycles, driving cycles explain how the vehicle, or actually we will focus on vehicles here because that's where we normally come into contact with hybrid powertrains, but driving cycle could of course be on whatever. It could be not only a vehicle, it could be a machine or any kind in industry. But these slides are focusing on vehicles then. When the powertrain is dimensioned, it normally is addressed to suit a specific driving cycle. And there are two different kinds, you can say. You have internal driving cycles at the companies, which include things like, I wrote here, top speed, acceleration, durability, etc. For instance, if you're producing a sports car, maybe you have a driving cycle that it should be able to operate at 200 kilometers per hour continuously for 2 hours or something. This is not something that is wished by the legislation. So, for instance, EU, Japan, US, Asia, they have different driving cycles, and that's normally due to legislations. And it's to be able to compare different things between different manufacturers. So here are a few different types. NEDC, which is the New European Driving Cycle. This is the standard driving cycle for vehicles, light vehicles, cars in Europe. And there are others like UDC, Urban Driving Cycle, WLTC, World Harmonized Light Duty Driving Test Cycle, which is used outside of Europe. And we have some other, you have one from Japan, the 10-15 mode cycle, etc. And then you often use this for standardizing and enable comparison of fuel energy consumption. Basically, if it's a gasoline or diesel car, it's the fuel consumption, and if you have a hybrid or electric car, it's the energy consumption. And this might lead to sub-optimizations, and the vehicle could then be optimized for specific markets. Sometimes that's called, it's a cycle biter. So you make the vehicle so it has the lowest possible fuel consumption when you are using it in that specific driving cycle. But if you drive it in another driving cycle or in real traffic, then it might differ quite a lot. And these driving cycles, they are, as we said, they are different. Here we can see the NEDC and the WLTP, which are two very common cycles. And you can see there is a difference in, for instance, duration, distance, and the distance is especially important for plug-in hybrids because it controls how much you can run on pure electric drive and how much you need to utilize your ICE. There is a difference in speed and a different time of standstill. And also there are other boundary conditions such as demands of temperature and approved modifications of the vehicle. Basically, if you don't say that you can't change this, the vehicle manufacturer will change it if they benefit from it. So in many, especially the older driving cycles, like the EDC, before we started with the new European driving cycle. You can change the tire pressure, you put tape over door gaps to reduce the wind resistance, etc., etc. So you modify the car quite a lot to reduce the fuel consumption when driving in this driving cycle. And that of course meant that it was quite a large difference between the standardized fuel consumption and the real consumption in real traffic. So the newer driving cycles, they have taken away the possibility to do these modifications, and they are closer to real traffic fuel consumption or energy consumption. Example of a hybrid powertrain dimensioning using a simplified driving cycle approach. Well, as I understand, if you have an NDC cycle, you need to have a more sophisticated simulation model, but you can get quite far by making a simplified powertrain dimensioning like we will do here. So if you imagine that you have a specific car, which is considered to need an average power of around 10 kilowatts during highway driving and around 50 kilowatts during city driving, which is normal, okay values, you can say. And then if you have a driving cycle that says that this car is used 40% for highway driving and 60% in the city, then the average power will be then 10 times 0.4 plus 50 times 0.6, meaning that the average power is 34 kilowatt. And that's then the smallest possible ICE power in a hybrid powertrain, as long as the accumulator is large enough to supply the vehicle energy when the power demand is higher than the ICE maximum power. So you need to have a large enough accumulator as a buffer, otherwise you will have to increase the average power, you have to increase the ICE maximum power. So you have to have a larger ICE engine if you have a smaller accumulator. When this powertrain is then used for highway driving, the excess power, meaning 34 minus 10 kilowatts, 24 kilowatts, will be used to charge the accumulator. And when the accumulator is fully charged, the ICE can be shut down and the car can run on electricity. But if the car is used more in the city than expected by this driving cycle, the accumulator will after a while be fully discharged, and only the ICE's 34 kilowatt will be available to power the car, since there is no extra energy that you can use for instance, accelerations in the battery. So then you will have a quite limited performance of the car when the battery is drained. So when is then hybrid technology extra beneficial? Well, first of all, in city driving, when you brake, and you can save the brake energy in the accumulator, and when you have a lot of acceleration, then you use the saved brake energy from the accumulator. And if you compare this to an ICE powertrain, when you brake, the brake energy goes into heat in the brake discs, and you can't use that for anything. And when you accelerate, you have to put new energy, meaning fuel, into the system, because you have wasted all the brake energy. With hybrid technology, you can also get rid of exhaust emissions in, for instance, parking buildings or city centers. It's quiet, so you can run it in stealth mode. Can be useful in other applications like military applications. But if you compare this to electric vehicle, basically you have the same benefits as for a full electric vehicle with the hybrid vehicle. But the extra benefit from a hybrid vehicle is that you have a longer driving distance possible, without that you need to stop and charge the battery now and then after every 350 kilometers or something. This also means that you have a smaller accumulator, which means that it's cheaper, since the accumulator is still so expensive. That's the reason why the electric car is expensive. So even if it's in a way much more complicated with a hybrid car, it's mature technology with the ICE, so it still becomes cheaper. And you can still use it like a plug-in hybrid for most of the everyday driving if you don't drive that far, like going back and forth to work and to the shop, etc., etc. There are also some possible secondary benefits with hybrid technology compared to an ICE powertrain. You can have more power, that's always fun. Electric motor plus ICE from if it's a parallel hybrid, it gives you much more power. You can have AVD. For instance, you have a possibility to have the ICE powers the front wheels and an electric motor that powers the rear wheels. And then automatically you have an AVD system, all-wheel drive, which gives you better traction and handling. With several motors you can have torque vectoring. More electric motors that enable a relative simple distribution of torque. For instance, if you have an electric rear axle, as we mentioned above. Torque vectoring means that you can put more or less torque to the right or the left, meaning that it helps you with the handling in when you are going into curves, for instance. But the note here that these benefits are also common with electric cars where you have more than one motor. So they are benefits with hybrid cars, but they are also existing in electric cars. Different types of hybrid powertrains then. If you start with a series hybrid could be seen as an ICE with an electronic transmission and an accumulator which can be used as an energy storage or an energy supply, depending on if you are producing more power than needed with ICE or less. This is sort of like a diesel electric locomotive with an accumulator. But what's a diesel electric locomotive then? Maybe you are familiar with that. Many diesel locomotives like this T44 in this figure are diesel electric, meaning that they have an electric transmission. They don't have the possibility to store the electric energy, but they use a generator and an electric motor as an electric transmission instead of normal gearboxes with different gears. So it's like a diesel powered electric generator that generates electric power to the electric motor that powers the wheels. So if we then add an accumulator to the electric transmission in series with the power generator and the electric motor, we have a series hybrid. The power from the electric generator can then go either directly to the electric motor or through the accumulator. The power generator consists basically of an ICE and an electric generator. All the power from the ICE is transmitted to the wheels via electricity in the series hybrid. So there is no gearbox that transmit the power, only mechanically. In a parallel hybrid, the ICE can either power the wheels via electricity in the same way as in the series hybrid, the red arrow in the figure, or power the wheels directly through a mechanical transmission, a gearbox, like the blue arrows in this figure, or they can do both at the same time. So this opens up for using a mechanical transmission when that's most effective, and you can also use the red part in this figure, actually the series hybrid part, when you need to store electricity in the accumulator. So this opens up for a better utilization of the powertrain in normal driving and the driving cycles we discussed previously. A plug-in hybrid is where an accumulator also can be charged from the electric power grid, and this is the normal case nowadays. A plug-in hybrid could of course be both of a parallel or series type, but most often they are nowadays in the parallel type. Often you have a higher accumulator capacity if it's a plug-in hybrid compared to if it's a non-plug-in hybrid. So we get most use of this plug-in feature, meaning you can drive it on pure electricity for maybe 50 kilometers, and then that's why you need a larger accumulator. So when are the different types of hybrid powertrains most beneficial? Plug-in is best when you have shorter distances and access to many charging stations. For instance, when you commute to work, shorter distances, then you can use it as an electric car. And then you still have the possibility to run longer distances with the ICE when you need that. Series hybrid mainly works for city driving when you have a lot of acceleration and a lot of braking sequences. And parallel hybrid works both with city and highway driving because you have the mechanical option, the mechanical transmission that gives higher efficiency on highway basically. And this also means that nowadays the normal hybrid is plug-in hybrid of a parallel hybrid type. So we have the possibility to charge it at home, and you have both the possibility to operate the wheels or power the wheels to only electrical power or also mechanical power. What types of internal combustion engines are used? Well, basically it's the gasoline or the diesel engine. The gasoline engine is the most common in hybrid powertrains. It enables a smoother integration with the electric powertrain, so you basically don't feel when the ICE is starting or stopping. This can be really smooth and very good nowadays. And also the gasoline doesn't suffer from the nowadays bad reputation of the diesel engine. I guess you all know about this, but the diesel engine was sort of the most environmental friendly option until around 2015, when something which was called Dieselgate came, when it was shown that the diesel engines gave more NOx emissions. But actually this has been well known ages before that. So, but it came up and it was then public knowledge, and then suddenly the diesel engine wasn't as popular anymore. You can read more about this if you Google it. I put a link on Wikipedia here, you can see something if you want. The diesel engines are, of course, as we know, the most fuel efficient, so that they maybe in many hybrid could be much better than the gasoline engine, but they are not as common in the hybrid powertrain as the gasoline engine. Basically because of these two things, it's not an as possible smooth integration. You might feel when the diesel engine start and stop because it will be a little bit rougher activation, and also since many hybrids are sold with an environmental friendly approach, or you don't want a diesel engine because that isn't thought of as environmental friendly anymore. How is the electricity stored then? I have been talking about accumulators. I won't go into this into detail, but there are different technologies, of course. We have the standard car battery, lead acid. It's a good battery for starting the ICE, but it's not the best for a hybrid car to store more energy. We have the nickel cadmium, which is an old technology, isn't used anymore. We have nickel metal hydride, and this is a good battery for many things, basically because it has the same voltage level, 1.5 per cell, as a non-chargeable battery. However, nowadays we have the lithium ion, which is the best battery for storing large energy levels. It is light, it is durable, however it is still very expensive, and that's the biggest drawback with the lithium ion. Also supercapacitors exist, however these aren't as common nowadays since the lithium ion batteries has become so much better. So basically it is the lithium ion battery that is of interest and is used in hybrid and also electric powertrains.